Hello, welcome to another module in this massive open online course. So, we are looking at the Fourier analysis or Fourier transform for continuous time and aperiodic signals, and we are looking at the properties of the Fourier transform. So, let us continue looking at the properties. We have looked at the time reversal property, that is, if x t has a Fourier transform x of omega, capital X of omega, then x of minus t has the Fourier transform capital X of minus omega. All right. So, let us continue our discussion on the properties on the properties of the Fourier transform, and let us look at another property which is known as the duality, or the what is also known as the symmetry property of the Fourier transform. And what we mean by this is as follows, that is, if x of t has the Fourier transform x of omega. Okay. Now, what can we say about the Fourier transform of x of, what can we say about the Fourier transform of the signal capital X of t? And to understand that, let us first start with the inverse Fourier transform, that is given as 1 over 2 pi integral minus infinity to infinity x of omega e raised to j omega t d omega. Now, what I am going to do in this relation above, that is the inverse Fourier transform, I am going to interchange the roles of omega and t, that is replace omega by t and replace t by omega. Okay. So, remember, this is the inverse Fourier transform, inverse f t interchange the roles of t and omega, and then what we are going to have is x of omega is 1 over 2 pi minus infinity to infinity, replace omega by t, x t e raised to j omega t will remain t omega, or basically only omega t dt. And now, if you look at x of minus omega, x of minus omega will naturally be 1 over 2 pi minus infinity to infinity x of t e raised to minus j omega t dt, which basically implies that 2 pi x of minus omega is integral minus infinity to infinity e raised to minus j omega t dt, and this is nothing but the Fourier transform of x t. So, what we have is that capital X t has the Fourier transform 2 pi small x of minus omega, where small x t has the Fourier transform capital X of omega, and this is known as the symmetry or the duality property. Okay. This is known as the duality property, or also the symmetry of the Fourier transform. So, what we see is that capital X t has a Fourier transform, that is 2 pi small x of minus omega. Okay. So, let us look at a simple example to understand this. For example, just a very simple example, we know that delta t has the impulse has the Fourier transform 1, which means delta t minus t naught, that is by the time shifting property, impulse that is shifted has the Fourier transform e raised to minus j omega naught t into 1 equals e raised to minus j omega naught t. Let us call this as your x of t and let us call this as your capital x of omega. Now, using duality, what happens is we have capital X of t equals, replace omega by, I am sorry, this will be omega times t naught. Replace omega by t, so this will be minus j t naught. So, we have e raised to minus j t naught has a Fourier transform 2 pi x of minus omega, where 2 pi delta of x of t is delta x, small x of t is delta t. So, this will be delta of minus omega 2 pi delta of minus omega minus t naught, which is nothing but 2 pi delta omega plus t naught, that is delta minus omega minus t naught is basically the impulse located at omega equals minus t naught. So, which is the same thing as delta of omega plus t naught. Okay. So, basically what we have using duality is that e power minus j t naught has the Fourier transform 2 pi omega plus t naught. Now, replacing t naught by omega naught, we have e raised to minus j omega naught t has the, or replacing it by minus omega naught. So, we have e raised to j omega naught t has the impulse response delta of omega minus omega naught, that is e raised to, that is the complex exponential e raised to j omega naught t. This is an impulse located at omega naught scaled by 2 pi. Impulse located at omega naught scaled by 2 pi. Okay. So, what we have shown is that the complex exponential e raised to j omega naught t has the Fourier transform 2 pi delta omega minus omega naught, and this we have demonstrated using the property of duality. Okay. All right. All right. Let us look at some other simple properties. For instance, we have differentiation in time. Let us say we have x t as the Fourier transform x omega. What can we say about dx t over dt? What is the Fourier transform of this quantity? And we can see this again. Let us start with the inverse Fourier transform. This is minus infinity, in fact 1 over 2 pi minus infinity to infinity x of omega e raised to j omega t d omega dx t over dt equals 1 over 2 pi d over dt of minus infinity to infinity integral minus infinity to infinity x omega e raised to j omega t d omega. Now, interchanging the order of, so now moving the differentiation inside the integral, we have this is equal to minus infinity to infinity d over dt x e raised to j omega t d omega, which is nothing but 1 over 2 pi minus infinity to infinity x omega. Derivative of e raised to j omega t with respect to dt is e raised j omega times e raised to a j omega t times e raised to j omega t d omega. And now you can see this quantity is the IFT. This is IFT, the inverse Fourier transform of j omega x omega. Therefore, this implies that your the derivative, time derivative dxt over dt has the Fourier transform x of omega. This is the Fourier transform of the derivative. This is the Fourier transform of the derivative. Therefore, what we observed is that differentiation in time is analogous to, is basically equivalent to multiplying by j omega in the frequency domain. So, if you differentiate in time, the corresponding Fourier transform the corresponding Fourier transforms obtained by multiplying by j omega. Okay. Now, similarly, we also have differentiation in frequency, which obviously you can guess will be an analog or a dual of this, that is differentiation in frequency Now, when you differentiate in frequency, it can show that if x t signal small x t as Fourier transform x of omega, then minus j t x t has the Fourier transform d over d omega times x omega, d over d omega of x omega, that is the derivative of x omega, all right, the derivative of x. That is, if you differentiate in the frequency with respect to omega, the corresponding time domain signal is multiplied by minus j into t. So, minus j t small x t has the Fourier transform, that is the derivative d over d omega of x of capital X of omega. Okay, and you can prove this similar to the proof for differentiation in time. Okay. Now, let us come on to one of the other properties, that is the integration in time. The integration in time, which is basically, if you look at this, that is, if you consider the signal, let us say x t has Fourier transform x of omega, then you can show that the integral of this, integral minus infinity to t x tau d tau, this has the Fourier transform pi x of 0 into delta omega plus 1 over j omega into x of omega. This is the Fourier transform when you integrate the signal in time. Okay. This is the Fourier transform when you of the integral in Fourier transform of the integral in time. Now, we come to another important property, that is the convolution property of the Fourier transform. Now, the convolution property of the Fourier transform, this is as follows, that is, we have x1 t which has the Fourier transform x1 omega, okay, and we have x2 t which has the Fourier transform x2 omega. Now, what can we say about, well, x tilde t which is the convolution of x1 t into x2, this convolution of x1 t and x2 t. So, remember this is the convolution operator. So, we have x1 t which is the Fourier transform capital X1 omega, x2 t small x2 t which is the Fourier transform capital X2 omega. Now, we want to see what is the Fourier transform of the convolution of these two signals, that is x tilde t which is the convolution of x1 t with x2 t. And this can be derived as follows, or this can be shown as follows, that is, you have x tilde t equals convolution of x1 t with x2 t, which is basically, I can write this as minus infinity to infinity x1 tau x2 t minus tau d tau, and therefore, the Fourier transform of this x tilde omega, this will be minus infinity to infinity, well, x tilde t e raised to minus j omega t dt. Now, substitute for x tilde from above, that is, you substitute expression substitute for x tilde t, this will be integral minus infinity to infinity integral minus infinity to infinity. Well, I am first substituting for x tilde t. Now, x tilde t will be x1 tau x2 t minus tau e raised to minus j omega t d tau, inner integral is with respect to d tau, outer integral is with respect to t. Okay. Now, what we do is, now we interchange the order of integration. Now, if you interchange the order of integration, what you will observe is this becomes, the outer integral will become with respect to tau. So, this will become, and it does not depend on t. So, you have x1 tau, and the inner integral will be minus infinity to infinity x2 t minus tau e raised to minus j omega t dt times d tau, that is, outer integral has now become with respect to tau. Now, if you look at this, this is the Fourier transform. You can see that this is the x2 integral minus infinity to infinity x2 t minus tau e raised to minus j omega t dt. This is nothing but the Fourier transform of the delayed signal x2 t minus tau, that is, x2 t delayed by tau. Therefore, the Fourier transform of this will be capital X2 omega, correct, into e raised to minus j omega tau. Okay. So, this is the Fourier transform of the delayed signal x2 t minus tau, and the x f t is Fourier transform of x2 omega e raised to minus j omega tau, which is equal to, therefore, minus infinity to infinity x tau, substitute x omega or x2 omega e raised to minus j tau d tau. Now, x2 omega does not depend on tau, so that comes out of the integral minus infinity to infinity x tau e raised to minus j omega tau. And now, you can see this quantity integral x tau e raised to minus j omega tau d tau. In fact, this is nothing but x1. I am missing an x1 over here at every place over here, that is x1 tau. So, this will be x1 of omega, and in fact, this is x2 of omega. So, at this point you have x1 omega times x2 of omega, and that is your x tilde of omega, which is the Fourier transform of the convolution of two signals. So, therefore, finally, what we have is that x1 t convolved with x2 t has the Fourier transform x1 omega times x2 omega, and therefore, what we can see is that convolution in time leads to multiplication in the frequency domain. And this is something that we have seen many times before at this point, which is very interesting, which is one of the most interesting properties. So, on the left you have convolution in time, and on the right you have multiplication in the frequency domain. So, when you convolve two signals in the time domain, the corresponding Fourier transforms get multiplied in the frequency domain. Alright, and this is one of the most interesting and important properties which makes the Fourier transform very useful, and analysis with the Fourier transform very tractable or very convenient. Okay, all right. And similarly, one last property which is the dual of this, that is the multiplication, that is what happens when you multiply in time that is similar to previous scenario. You have x1 t which has the Fourier transform capital X1 omega, x2 t which has the Fourier transform x2 omega, then x1 t into x2 t, that is the multiplication of these two signals has the Fourier transform 1 over 2 pi x1 into I am sorry 1 over 2 pi x1 omega convolved with x2 omega. Okay. So, you have multiplication in time naturally leads to convolution in frequency. Multiplication in time that leads to convolution in frequency, in the frequency domain. All right. So, what we have seen in this module is we have continued a discussion of the properties of the Fourier transform. We have looked at the differentiation in the time and frequency domains, also integration in the time domain, and we have also looked at the convolution property of the Fourier transform. All right. So, other aspects in the subsequent modules. Thank you very much.